So in this video, we're going to start talking about section 4.3, which is called the coefficient of determination. So there's only one objective in this section, and it's to compute and interpret the coefficient of determination. Okay, and this is probably all new stuff that you've never seen before, so we're going to take a couple days to get through it. So the coefficient of determination, r squared, measures the proportion of total variation in the response variable that is explained by the least squares regression line. So again, you've seen regular old r before. R is the correlation coefficient, and now if you take that number and square it, you're going to get something called the coefficient of determination. Okay, and what this really is it's again a proportion. And this is important. So what I'm writing, please make sure that you also write, because it's going to come up in a formula that we're going to look at tomorrow. So what this really is the explained variation over the total variation. Okay, and the coefficient of determination is a number between 0 and 1 inclusive. That is, r is less than or equal to r squared, which is less than or equal to 1. Remember, regular old r, the correlation coefficient, that was always a number that was between a -1 and a +1. So if we're taking that number and squaring it, remember, if you square any negative number, it's going to become positive. So that's how we get this 0 on that left-hand side instead of the negative number there. Okay. Keep in mind as well, with the correlation coefficient, if you had r equals 0, that means your data had no correlation at all. Your dots, when you looked at the scatter plot, were all over the place. So it's kind of the same thing here. If r squared equals 0, the line has no explanatory value. In other words, you can't get a line that's going to explain that data. And in the other case, if r squared equals 1, that means the line explains 100% of the variation in the response variable. In other words, every single one of your data points is going to lie on that regression line. So we're going to come back to the same old example that we've been doing. Hopefully it'll start to click when we keep talking about data that's the same, because we've been plugging it into the calculator over and over again. So the data at the right are based on the study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which drilling begins is the predictor variable, it's x, and time in minutes to drill is the 5 feet is going to be your y variable. Again, the important thing here is that you have the 5 feet. So it's time to drill 5 feet. That's going to be the key to the one of the problems that's going to come up in a second. So again, x is feet, y is time. Okay, so again, if I were to look at a scatter plot of that data, this is what it would look like. And in the last section, we had already found all of this information. Hey, if we're looking for the mean and the standard deviation, remember we went in and we did stat calculate option number 1. And we had x with a bar, and then this was our sample standard deviation. And then we did the same thing with our time. And again, even though in the calculator it's going to say x again, we were talking about our y variables. So we had our mean for y, which was 6.99, and our standard deviation for y. Okay, and we also found the correlation coefficient. Again, that was when we did L1 and L2, and we looked at it together by using stat calculate and option number 4 to get that correlation coefficient. Okay, and in the last section, again, we had already found the equation of this regression. Okay, and again, it's down here. It just looks a little bit different. Okay, in the last one, we had y with a hat equals 0.0116 x plus 5.53. Okay, so now all I did was take out y. Again, y was time, so I plugged in time. Okay, and just trying to trick you here, all I did was flip-flop. Remember, addition is commutative, so you can flip-flop it. So flip-flop those two things, and again, x was depth, so I took out the x and I just put in the word depth. Okay, so we're going to answer these two questions, and they're going to pop up on our next slide here. As a matter of fact, I'm just going to click to the next one. I couldn't get rid of this slide. Okay, suppose we are asked to predict the time to drill an additional 5 feet but we did not know the current depth of the drill. What would be our best guess? Okay, so again, if you know nothing else about the problem and you want to know how long it's going to drill that 5 feet, again, that's going to be the average of what you were looking at. Okay, and we just found our average earlier was 6.99. Again, remember, in the question itself, it said the time to drill 5 feet. So that's why we don't have to do anything else. It's just the straight mean. So it's going to be 6.99 minutes. Okay, but now suppose if we are asked to predict the time to drill an additional 5 feet if the current depth of the drill is 160 feet. So again, depth, feet, that's our x value. So all we're going to do is take our linear regression equation, which is y with a hat equals 5.53 plus 0.0116 times our depth, which again, I took out depth and plugged in 160. And when you chuck that all into the calculator, you should get an answer of 7.39. So our guess increased from 6.99 minutes to 7.39 minutes based on the knowledge that the drill depth is positively associated with drill time. In other words, it's going to increase a little bit the deeper that you get. Okay, so with this slide, we're going to do like 3 or 4 more slides. And this is going to be the slide where we're going to pick up with tomorrow in class. And hopefully it'll, again, start to sink in. So all I did on this slide was draw our linear regression line, which again, remember, that's the y with a hat. And I drew our average y, which was 6.98 or 6.99. Okay, and that's that red line. Okay, and now if I were to look at any point on that line, okay, and I look at how to get from here to here, okay, that would be the difference you would subtract to get the distance from here to here. You would subtract to get the distance from here to here. And again, it's only the y values that I'd be subtracting here. Again, that's a vertical distance. You're not moving it all in your x direction. It's just vertical. So the only thing that we care about here is our y values. So again, we have y with a bar and our y with a hat. Okay, and look at what the words say here. Above your line is the difference unexplained by the drill depth. And on the bottom, we have the difference explained by the drill depth. So the difference between the observed value of the response variable and the mean value of the response variable is called the total deviation. And that's going to equal y, equals y minus y with a bar. I got ahead of myself there. Okay, so that's what your total deviation is going to equal. And the difference between the predicted value of the response variable and the mean value of the response variable is called the explained deviation, and that's going to be equal to y with a hat minus y with a bar. Okay. And there they are. Again, I typed them in there. So the difference between the observed value of the response variable and the predicted value of the response variable is called the unexplained deviation, and the unexplained deviation is equal to y minus y with the hat. Okay, so again, if we're looking for the distance between points, again, you're subtracting, and again, from that picture, we know that this is a vertical distance, so that's why we're subtracting our y's again. So again, when you come in tomorrow, I'm going to start with that slide that had the picture on it. We're going to re-go through these last 3 slides about unexplained deviation, total deviation, and explained deviation. And then we're going to move on to talk about what that coefficient of determination actually represents.